Are we ready?
Yeah.
Yes. Happy Friday. We've made it. We're more than halfway through the semester. Like 2/3 of the way through, something.
Like that.
How many do you have? 16?
But that it's I think it's 15, but that includes finals.
Does it include Thanksgiving too?
It does include Thanksgiving also, so it's really like 14 weeks. 13 weeks of class. And then a week of finals. Thanksgiving in there too.
11 is pretty much 10. So
We're done! Wrap it up, guys. Well, we are in like the last note packet is the least mathy, most computer sciencey, so most of you will enjoy that. Emily and I will be miserable, but that's okay. But yeah, so this is like, and we have the biggest idea of proofs that we're going to talk about in just a little while, hopefully today. So we are we're nearing the end of what I get to teach you in this class, which is sad for me, but maybe good for you. Okay, we are on page 10, and I think that exercise 9 is the thing we did not do yet. So we have been looking at composition, or we did that on Monday. We were looking at composition of functions, and so that homework 9, the like whole first page you can do now. But I do this weekend maybe, and then ask a question about it on Monday. So if we have f from x to y and g from y to z, they're both surjective or onto, then g of f is surjective. So my total gut instinct is to just jump in and write a proof because I have no idea how to do scratch work for this, but I know that that's the wrong choice. So I'm going to try to do scratch work. Yep. You're welcome. Here are my bubble diagrams. They got progressively weirder, but that's all right. We are looking at g of f, so we've got f first and g second. We are saying that this is onto and this is onto. Does it follow that this is onto? So how do we do a proof, an onto proof? If I want to prove that g of f is onto, how do I do an onto proof? G of f goes from x to z. Y'all are tracking that with me. This is x, this is y, and this is z. So G of f takes the set x, maps into or onto the set z. We're trying to figure out if it is into or onto. How do we do an onto proof? Yep, so we're going to pick a little z in big Z. And what do we want to show with that? That it has a preimage in x. Yeah? So we picked an arbitrary element in the big target, and we want to show that it has a preimage in the very first set. So we want to show there exists an x in x such that g of f of x equals z. That's like what we're going for. The preimage thing, that's a preimage. Okay, so what do I know about this element z in big Z? What do I know about it? It's what? As a preimage where? In y. Why? Because what's on 2? Yep. So there exists a little y in big Y such that g of little y is equal to z. Because g is on 2. Okay. So there's a y in big Y where g of y equals z. What's true about that little y? Yeah, f is onto as well, so it has a preimage in x. So there exists an x in big X where f of x equals y, and this is again because f is onto. And yeah, and then we're done. I can't write it here because I don't have space, but I'll write it in proof. Because then this y is f of x, so you're looking at g of f of x equals z, so x is the preimage for z. Does that make sense? Yes. Okay, let's write a proof. We are going to let f from x to y and g from y to z be onto functions. We will prove g of f from x to z is onto as well. Welcome.
Sorry.
No, you're
I forgot
fine.
my pen, so I had to
Those
go
are the
buy-
best
Yeah,
pins.
I had to go buy some.
Nice. Can I buy some off of you?
Yeah, I'm not charging them.
Oh gosh, rude. I don't get some sort of discount for being your teacher.
You get a discount, but it's like a reverse
Still-
discount.
Oh. Sorry, I asked. Which is an upcharge. Okay, so we have this g of f is going from x to y. It is also, we are going to prove that it is onto. So we are going to let little z, that's not, y'all, no, this goes to z. Everybody's with me now? Nobody caught that mistake I made there? There we go. It's Friday. It's hard for me to teach this class on Fridays. I look forward to it because I have fun teaching y'all, but it also requires my brain more than any other class that I teach. And it's gone by Friday. Or maybe all the time, Michael. I don't know. It might be gone all the time. I don't know. It's just more noticeable when I'm here. We're going to let Z be in big Z, little z in big Z. And we're going to say something like, since G is onto, there is a y in big Y such that G of little y equals Z. Now, y is in big Y and f is onto, so there is an x in big X such that f of x equals y. Notice g of y equals g of f of x, which is equal to z. Maybe I should write that backwards. I'm going to write that differently. Sorry. G of f of x is equal to g of y, which is equal to z. So we found, oh gosh, x in big X such that g of f of x equals z. Thus, g of f is onto. I have a fair warning for you. I do not have enough space on most of the things we're going to do today in your note packets. But I didn't know that till I tried to fill in mine and couldn't fit what I needed to in the space I had provided. So that'll be a fun little adventure. Do you have any questions about exercise number 9 on page 10? Does this make sense?
Yes. Yes.
Okay. Are you going to get pens too?
No, I'm gonna get a snack. My stomach is like growling.
Get your snack. I'm not judging you. Go get your snack. You need your brain energy for your test in an hour. Go get a snack. Get me one too. Okay. Number 10 is on your homework, so I'm not going to do it for you. It's on homework. What is actually homework number 9. Have fun. All right. Number 11. There is not enough space here for this, but that's fine. We're going to do our best. If F and G are both bijective, then G of F is bijective. This makes sense, but let's prove it. Cool? Okay. I'm just going to prove it because I don't have space to do scratch work. Is that okay?
Yeah.
How do you prove something's bijective or that it is a bijection? Yep. 1-to-1 and onto are surjective and injective. So we are going to let F from X to Y and G from Y to Z be bijections. We will prove G of F is also a bijection. No. I think it's a good idea to remind yourself what the heck you're doing sometimes. And also your reader. I don't know.
So as soon as she leaves, you stop doing scratch work.
Yeah. She's gone. She can't give me any grief about it. She'll come back and we'll be, we would have been finished with scratch work anyway. Sorry. Okay. So I'm going to do first 1-to-1 if that's okay. So I am going to write down the sets where this goes. So G of F goes from X to Z. I'm just doing that for myself. You don't have to change that, but I got to know where I'm picking elements from. So we are going to let, we're starting in X. So we're going to let A and B be in X and assume G of F of A equals G of F of B. What are we trying to show when we're showing that G of F is 1-to-1? What are we trying to show? That what equals each other? No, that would be onto would be that range equals codomain. 1-to-1 means that 1-to-1 is that you have two darts that landed in the same spot. You assume they landed in the same spot, and what you want to show then is that they're actually the same dart. So what we want to show is that A actually equals B. It's not just that they landed in the same spot and were different darts, it's that they're the same dart. So we want to show that A equals B. That's our target, to show that this is 1-to-1, that the composition is 1-to-1. How do we do that? What do we know? What do we know about the functions we're working with? Why is f of a equal to f of b? Start there. Why does f of a equal f of b? I think you have the right idea. We got to word it better, yeah.
Because they're f of a, if you use the function on the inside, that took it to
Michael, I don't know what that means either. I'm ready.
If f of x, since f of x is equal to y, that means that they would have to be.
You're on the right track. Thoughts? Anybody? If we had an equation, but we don't.
So we're plugging into G.
Sure. What's true about G? And in particular is it is 1-to-1. So if G of f of a equals G of f of b, then f of a has to equal f of b. Those are y's that are in the domain of G. Yeah. The ideas are there. Wording, yeah, right. So this means that f of a equals f of b, and this is, because G is 1-to-1. And then from there, you get that a equals b because f is 1-to-1. Does that make sense?
Yeah.
So we are done. That means that G of f is also 1-to-1. So since a equals b, whenever G of f of a equals G of f of b, G of f is 1-to-1. Okay, so we showed the composition is 1-to-1, and now we want to show that it is onto. How do we show that something is onto? Remember, this function's going from the big function is this composition that is going from x to z. So how do I show that that big function is onto? Yep. All right, so we are going to let little z be an element in big Z, and we want to find its pre-image. But we just did this, right? Can I just say we just did it? As proven in exercise 9, G of f is surjective. Maybe this, as proven in exercise 9, there exists an x in big X such that G of f of x equals z, and thus G of f is onto or surjective. Now, G of f is both 1-to-1 and onto, and thus a bijection. Do we feel okay with this?
Yes.
Any questions? Brian, are you here with us? No. When was the test? Was it today? This morning? Well, I'm glad you're here, even if it's only physically. And I remember it. It wasn't, yesterday, but I remember. Just show up when you can, right? Mentally, if possible. And it's not always possible. Okay. Any other questions about page 11?
This is following.
What?
Prove the following.
Oh, Lord. How am I going to remember to see this? Ah! There we go. Thank you. Okay, I've got to figure out how much I want to do with this. Basically none, but let's do it anyway. We're going to do scratch work. Then scratch work. Otherwise, give a counterexample. We shall do that. So we've got f from x to y, g from y to z. They're both functions. We're going to see if these statements are true, and if they are, we are going to prove them. And if they are not, we are going to find a counterexample, which disproves them. Okay, g of f is injective. G of f is 1 to 1. Is f 1 to 1? Or must it be? Okay, so this is the thing we're trying to prove. So let's start there. If f is injective or 1 to 1, how do we do that proof? We would let what happen? I want to prove that f is injective. How do I prove a function f is 1 to 1? You choose two things in your domain and assume their target is the same. So we're going to assume f of a equals f of b. What we want to show is that a has to equal b then. Okay, so I can't peel back that function. Like, I can't get rid of f because I don't have anything to actually plug it into, like Emily was mentioning a minute ago. Like, there's nothing really else I can do there. But I do know something about g of f, right? I do know that g of f is 1 to 1. So, and I also know that g is a function. So, like, these are both y's, but they're equivalent. You know what I'm saying? They're equivalent in here. And because g is a function, they have to go to the same spot over here. Every input has an output, right? 1. Yeah? So because g is a function, g of f of a has to equal g of f of b. Every time you plant an apple seed, you get an apple tree. My daughter asked me how the car works today. Mom, how does you pushing the pedals and moving the steering wheel make the car go? Well, there's a lot happening, but the wheels, me pushing the pedals makes the wheels turn, and that makes the car go. It pushes the car. And she was like, okay then. And if you were to push the pedal harder, it would go faster. Okay. All right. Have fun at the pumpkin patch. I'll see you later. Okay, so G is a function, because G is a function and those two things are equivalent, they have to go to the same place. So G of f of A equals G of f of B. But G of f is 1 to 1. That's the thing we got to assume, right? G of f is injective. So because of that, A is B, right? Not f of A, just regular old A is regular old B, because we get to peel away both of those things. So it's kind of strange. We need to get rid of the F, but to get rid of the F, we have to apply the G and then get rid of both of them at the same time. Did you say you get that? Good. And so G of F, because G of F is 1 to 1, A equals B, and then that means that F is 1 to 1. I disproved this next one. Let's see if we can do it again. These are new problems. They were fun for me to work when I was preparing for this, because I actually did that today. So, well, yesterday too. I was really going to make sure I didn't show up blind. Okay, G of F is, if G of F is injective, then is it true that G has to be injective or 1 to 1? So the function composition is, is 1 to 1. Wow, I don't even know. It's fine. This is F. This is G. This thing, G of F, is 1 to 1. So, I mean, think about this. You have this sort of thing happening. They have stopped in the middle somewhere, right? Is there a way to do something so that G does not also have to be injective? But the function, the composition overall still would be. So like this A and this B still go to 1 and 2, say. Is there something that we could do to G, the function G, to make it not 1 to 1? If I put another point here and just send it to one of these guys, right? Then the composition still, because the composition is going to ignore this because it doesn't exist in the domain of the composition, right? So the composition is going to ignore this guy. So overall, we would still have the composition would be 1 to 1. But that second part, G by itself, is not, because you have this third guy going to one of those other two. Does that work? Y'all have any questions? No. All right, on this one we have G of F. If G of F is surjective, then F is surjective. So I'm going to do the same kind of a thing, which I guess maybe tells you that I think this is a no. My bubble got really big there in the middle. Let's get rid of that guy. Let's just draw normal sized. Okay. I'm going to give up on pictures pretty soon. Okay, we're saying that this one is on 2. Is it true that this has to be on 2?
What are the ones in the middle? There's two of those up there.
What if what?
What if it goes like 2, 2, 3?
If it's 2, 2, 3, then the whole thing wouldn't be on 2.
Oh, that's right.
My example doesn't actually make sense. I'm looking at it right now and it doesn't make sense. I'm going to do some work right here to try to prove it now instead of trying to disprove it. Unless you have ideas about how to disprove it. Here's what I did, which doesn't actually make sense. I did this. No, not that. This. I guess maybe this would work. G of F would take this to here and this to here, which would be onto. F misses this guy. So not onto. Here's a counterexample. That works. 2, 2, 2, 3, 2. Yeah. Well, that looks nicer than the one I did. Okay, what do y'all think? Yes?
Yes.
Okay. So suppose that the composition is on 2. Does it mean that the second piece has to be on 2? What you got? Can't have that. Oh, I mean, you can, but that wouldn't be, the composition couldn't be surjective then.
It's,
1, 3, 1. But these have to go somewhere, which would mean they have to go there, so it would be on 2. Because they have to map somewhere. This is true, y'all. We need to stop trying to find a counterexample. Let's just try to prove it. How about that? Right. Counterexample does not exist because it is true. If we let, I don't know, what do you want to call these over here in Z? Z1, Z2? Do you want to call them something else? Oh, we just got to pick one. Okay, little z. Pick little z and big Z. The composition is onto, so G of F is onto. So there exists an X in X where G of F of X is equal to Z. Okay, so rewriting the g of f of x, it's g of f of x. F of x is an element in big Y, right? So there is a y in Y such that g of y equals x. Z, that's a z. I can't change to an eraser, but that's a z. So G is on 2. Questions? That one's kind of weird. Do you have questions about that? Your lack of responding to me today is, I don't know if it's a good thing, a bad thing, if it's a me thing, a you thing, an us thing.
It's biochemistry.
Yeah. I'm getting sleepy listening to myself talk, which is bad. I need y'all to help me wake up. I gotta teach polar coordinates again in a minute, so gotta really find it in me. Not to you.
Oh, I was just trying to remember what that was.
R and theta instead of x's and y's.
Oh, yeah.
You can do more in Cal 3. You're gonna take Cal 3, right?
I forgot what it
Because you're
was.
doing a math minor? Yeah. Darn right you should. You're doing a math minor too? Good. Math minor also? Why not? It's just 2 classes.
Linear.
It's Cal 3 or linear algebra if you don't pick up the minor. If you pick up the minor, it's both and one more class. The minor is Cal 3 linear algebra plus 1. The major is Cal 3 or, just computer science major is Cal 3 or linear. My husband's teaching Cal 3 next semester.
Pretty sure I'm in it.
Well,
I have it on my 4-year plan.
there you go. You take Cal 3 and linear. You're probably taking linear. Did you ever get your stuff worked out?
Yes.
Good.
They helped a lot. So, yeah, I'm now declared math major. I didn't know I wasn't.
Right.
So I decided to advise there. But also with mathematical statistics,
Mhm.
that's what it's called. What's
Mhm.
the difference between that and regular statistics?
You're going to do a whole lot more theory.
Medical statistics is like more calculus based.
Yeah.
Than probably stats.
Is there a first and second?
There is.
Is that offered in the fall?
One is in the fall and two would be in the
It's not offered next.
Yeah, one is not. One is, it's 1 in the fall and 2 in the spring. 346 in the fall, 347 in the spring.
Apparently two is every other spring.
Nuh-uh.
They're not doing it to the spring.
They're not doing it this. I couldn't find
I
it.
talked to Dr. Delston about it.
Will it fit in your schedule to do it in 2 springs?
Yeah, will it be available next year, right? So I'll
Yeah.
take it fall semester and the spring semester right after.
Okay. Okay, and you'll have to do that too? Okay,
So I'm in one right now,
right.
and apparently two is not.
Because half the people who have to take 346 don't have to take 347.
All
It's-
of them but me.
Yeah, it's only the math majors who have to take 347. I don't know who else is in 346.
It's all engineers.
Oh. That's why. It's only math majors who have to take 347 also. I don't know why. Maybe we should adjust that. Don't tell Dr. Greaves. Okay.
Best part is I have to know all that stuff anyway for chemistry.
Oh, well, that's good, I guess. Go ahead and pick up a math minor. Why not? Really?
In the CSU thing, it says for category requirements, pure applied math needed 1 requirement, and then linear algebra.
Or Cal 3 for the major, right? Or is that the minor?
Pretty sure it's for the major. I remember I was going through.
Cal 3 is part of the main requirements. You have to take Cal 1, 2, and 3. And then you need a pure applied math as well.
Okay, yeah. That's for the math minor.
Yeah.
That's why you got to take Cal 3. If you're doing the minor route, you got to take Cal 3.
Yeah.
And then one extra class.
Yes.
Okay.
It's worth it. Yeah. Yeah. Let's do it. And now you're really good at proof writing, so you're welcome. You're ready for that pure math class.
Yeah.
You probably should take the applied one though, just to, since you're computer people. That's applied math.
The reason
Computers.
is you have to take discrete as well as
Yeah.
the pure.
Right. Oh, so if you go the pure route, you only have to do one more.
Yeah, because discrete is part of pure.
Yeah. It's discrete and abstract, discrete and yeah.
But
Woo woo!
For the pure one, you have to take discrete and then a second pure math proof. There's only one extra class.
That's good. You got that. You had your advising yesterday though. You got to go talk to Dr. Hayes. Didn't you? Weren't you doing advising yesterday?
I did.
Or
Yesterday,
yeah.
Because I'm a transfer, so I
Right.
already have the Cal 30 credit.
Well, then you're ready. You just got to declare that minor and just check it off. You're done.
I didn't know it was
Yeah. Let's do it. We got math minors all around, right? Men majors. Those classes aren't similar at all.
I mean, it's calculus, right?
Mhm. Yeah, sure. Okay. Well, now we're ready to start 7.4. We're going to talk about cardinality again. You guys, we did cardinality a while back. They were all finite sets, so like these things. Cardinality, remember, is the number of things in a set. So the cardinality of this guy, the cardinality here is just 1. That's the number of things in that set is just 1. The thing is just A. What is the number of things in this set? It is also 1. Just the thing is the set containing A, which is strange. What is the number of things in this one on number 3? It's 2. It is A and the set containing A. How about number 4? Can you read through all of those curly braces? It is 3.
Yeah.
This is 1 element, 2 elements, 3 elements.
The comma helps too.
The commas help. How many commas you got? 1, there's 2 things, None, there's only 1 thing. It's not a trick.
Well, it's a nice little thing to notice. Why are there only 3?
Because all those curly braces. That comma means something different than the other commas. The 3 things are this, and then this. The elements themselves are A, the set containing A. I'm going to write the exact same thing down. And the set containing A, and the set containing A. This is helpful if I just write it again. Good. Great teaching today. Boy. This is a power set. Like, that's what's happening. It's the power set of... Oh, gosh. This is the power set of this set. No? Well, missing the empty set, but you were counting the empty set for me, right?
That's what
So we're going to move into sets that are not finite. So these are all finite sets where you can actually like count. You can get a number for the number of things in this set, but we're going to do some things where we can't. So for any 2 sets A and B, they have the same cardinality if and only if there is a 1-to-1 correspondence. That's called a bijection, remember. A 1-to-1 correspondence means it's going both ways. It is a bijection. So if we're looking, and like we did this already, right? When we were doing all of these examples, they have the some of them have the same cardinality, the same number of things in them, but we changed the one that we wanted to mess with, right? So it's like the same idea that we've been doing, but now we're going to prove it. That, well, we're going to get there. That two sets, if they have the same cardinality, then there's a bijection from A to B. Or if there is a bijection from A to B, then the sets A and B have the same cardinality. This is an if and only if statement, so it's a definition. So we are going to find a one-to-one correspondence or a bijection between those sets A and B. A bubble diagram. Well, I'm not going to draw bubbles because we've seen what they look like today. But this is A, B, C, and D. I want to map to W, X, Y, and Z in a way that is both one-to-one and onto. So I'm just going to go like this. I mean, you could be more creative if you wished. But the cardinality of A is equal to 4, and that is the cardinality of B. So there is a bijection between the two sets. Is that a pack of only black ones, or are there some that are multicolored? Corey?
It's just the black ones. Yeah, I didn't feel like splurging.
Oh, on the colors. Yeah, I understand. They are the best pins, though. See, I've got purple right here. I won't trade you because I need the purple one because I grade with it. No.
People grade with black.
No, they don't. Y'all write in black. I can't be grading in black. No one would see it. I do not grade in red. Have you ever seen me grade in red? No, it's very aggressive. I'm not that aggressive. There's some orange, okay? Orange is less aggressive. It's softer, except the one I use is not soft. It is very, very bright. But I can't use it any other time because I can't read it. Okay, how about, look at those straight lines. They look good. How about going from X to Y here? Well, the cardinality of X is what? Which doesn't equal 4, which is what the cardinality of Y is. So there is not a one-to-one and onto function between the two, which makes sense because you can't hit all of these guys. That one of those elements is going to be left out. And now for the most fun part of our whole semester. I'm just joking. It's not. But it is going to be fun. I'm going to use all of this space and probably some of this space to do this proof. Are you ready? So, y'all, there are levels of infinity. So there is what is called countably infinite, which means in theory that you could list them if you had infinite time.
I was literally about to say, yes, you know, your friend can count it to countable infinity, but we couldn't get to uncountable.
So, countably infinite means that you could, in theory, list them if you had no life and you had infinite time. Uncountably infinite would be that you can't list them all. There's no way to list them. So, and you're like, I don't know what we're saying, and that's okay. If something is countable or countably infinite, you can find a bijection to the integers because you're making a list, and so your list has a place value. Like this is first in the list, second in the list, third in the list, fourth in the list, right? And so you have you're drawing a bijection between your elements and the integers because you created a list with your no life and infinite time. The cool thing is that things that you wouldn't expect to have the same cardinality do, like the even integers and the integers. Those have the same number of elements. It's infinite, but it's countably infinite because I can list them all. given enough time and no life. Yeah?
Figure this out.
A canter. Canter.
Why something like that?
The textbook has, like, you know how sometimes it has like a picture of an old dude, typically an old white dude, who did a thing. There's a whole section. It's the Cantor diagonalization process is how we know that the real numbers are not countable. We're going to prove that in a minute. Well, we're going to do scratch word. But there's a whole like bit in the textbook, one of those like asides that's a history lesson. If you take history and math in the spring, that can count towards your math minor or major for you too.
Wait, so for real
Oh, you
numbers?
can't take it, can you? You can't. You can't take it in the spring and it won't be offered again while you're here. I don't think that you can. It's at the same time as some, no, it's been changed? Okay.
I know it was supposed to be the same time, but it's not. Register.
Well, Ryan was panicking about something, but okay. Maybe he got it moved.
For real numbers, would it not be countable because
It's not countable. I'll show you in a minute.
it's like a decimal, so it just goes to infinity in the decimal range versus,
For every one of them.
okay.
Mm-hmm. Okay, we are going to come up with a bijection between these two sets that shows that Z and 2Z have the same cardinality. Yeah? Do you guys know how to talk about the even integers? Like maybe a really good professor gave you a definition for the even integers, what every even integer looks like. 2x. Well, if we use the function f of x equals 2x. So if we let f, these are, I'm going to write this down, both countably infinite. Find bijection. So we will prove Z and 2Z have the same cardinality by finding a bijection between them. Let f from Z to 2Z be a function defined by, oh my gosh, f of x equals 2x. So what we're going to do is show that that is both 1-to-1 and onto. So I'm going to let A and B be in Z and assume that their image is the same, that f of A equals f of B. So what do we get from that? Yep. Then 2A equals 2B, and clearly A equals B. So F is 1-to-1. How do I prove that F is onto? Yeah, you didn't get your letters right, but I know what you mean. Yeah. So we're going to pick something in the codomain. So we are going to let y be an element in 2z. We want to find an x such that f of x equals y. Okay. Well, y is equal to 2x. We're there, yes? So y over 2 is x. Is this an element in z? Yeah. Y is even, so y over 2 is going to be an integer, right? We started with y is in 2z, so y over 2 is going to be in z. Is that okay? It would be a problem if we were like if they were both integers, because this isn't always an integer. It would always be real, but it wouldn't always be an integer. Just making sure that whatever this is fits this definition for whatever y is. And y is even, so it divided by 2 is still always going to be an integer. Consider x equal to y over 2, which is in z. Now, f of x is f of y over 2, which is 2 times y over 2, which is y. So we found x in z such that f of x equals y, thus y, f, is on 2. Since f is 1, 2, 1 and on 2, f is a bijection. Thus, the cardinality of z is equal to the cardinality of 2z. You have this on your homework. You have the opportunity to do this with us. Yeah, that you can call it O if you wish, that the set of odd numbers is the same cardinality as the integers. Be careful with how you define that function, going from which set to which set. What do you think about that? Kind of cool, right? I'm not going to do all of the proof for z and z plus, but this is also kind of weird because you would think it's half the size, right? If the integers have some cardinality, then the positive integers would have half that cardinality, but no. They're both countably infinite, which is wild. Okay, also the rationals is countable, which is crazy. So let's go with number 4. We're going to work on that first. We're going to take the integers and map to just the positive integers. So I'm going to draw the map. I'm going to draw the function, basically. Is that okay? I'm going to make a list of the integers. So I'm going to start at -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. This is z. I need to map to z plus in a way that is both 1 to 1 and on 2. So I can only list the positive integers one time, and I want to try to do it in a way that makes sense. I am going to map positive things to even numbers and negative things to odd numbers. So, or non-positive. So I'm going to map 1 to 2, 2 to 4, 3 to 6, 4 to 8, and so on. And then I'm going to go from 0 to 1, -1 to 3, negative 2 to 5. That just keeps shutting off for like half of a second and then turning back on, right? Did y'all notice? Have you noticed that? The air conditioner or heater or whatever is happening? So I would eventually list all of the positive integers on the bottom row and all of the integers period on the top row, and therefore with only one arrow going to or coming from everything, so it's both 1 to 1, non 2. And we can define this with a piecewise function. This is easy if I'm talking about the non-negatives. So I'm talking about positive. So when x is greater than 0, we're going to define that as 2 times the thing. If x is less than or equal to 0, though, I want to go to the odds. Yeah, but I can't use 2x plus 1 because that doesn't work if I plug in 0, then I get positive 1. Right? If I plug in 0. Oh, but that's what I would do want, is positive 1. If I plug in negative 1, this would be negative 1, though. Yes. If I plug in negative 1, this would be negative 2 plus 1, which would be negative 1, which isn't good. Yeah, I'm going to do, this is sort of like a negative correlation. I don't know. I'm going to do negative 2x plus 1 or 1 minus 2x. If you do that, so the 0 works, but the negative, oh my lord, that's an eraser. The negative 1 would give you 3, which is what we're looking for, because it would give you a positive 2 plus 1. This would give you a positive 4 plus 1, a positive 6 plus 1. Okay, so that's a bijection. We're not going to prove it, but you could. We are going to do, no, you could do this for all of the integers and all of the rationals. We're going to do it for only the positive ones so that I can, because it's easier to describe. What I'm going to do, because I told you guys the thing about making a list, if you can make a list of the things, then it's countable. So I'm going to make a list of the positive rationals. You ready? My list is going to go like this. It's going to be, I'm going to have rows and columns. The rows are going to increase in the denominator. These are columns. I am bad at talking, which is unfortunate with my chosen career. I'm going to increase the numerator here. You know, we've got like a matrix basically is what we're building. The row will correspond to the numerator and the column will correspond to the denominator. Did that make any sense at all? I don't know. Yes? Yes, no, maybe? Yes, okay. 3. This could go on forever that way. 4 over 1, 4 over 2, 4 over 3, 4 over 4. All right, and then this could keep going down this way too. And the fact that I could, in theory, if I had enough time and no life, then I could write this whole list, and that would be all the rationals, all the positive rationals, and that means it's countable. And you're like, I don't like this. Are you like that at all? Because some of those numbers are the same. You notice that some of those numbers are the same. 1 is listed 4 times so far, right? So what we're going to do is this thing where we sort of snake around, and we're going to like call the things in the list. So what you do is this. This is fun. This is weird. It's weird. So this is your first entry, 1 over 1. And you're going to go sideways. That's going to be your second entry. And then you're going to go diagonally. That's going to be your third entry. And then you're going to go down again, and that is going to be your fourth. And then we're going to move back up, skipping anything we've used before. So I have to skip 2 over 2 because I already wrote down 1. So this is going to be my 5th entry. Then I'm going to go to the side. That'll be my 6th. And then I got to scoot back down this diagonal, right? So I got to go back down this diagonal, right? Skipping any of the ones I have used before, which is none of these. So I got to hit all of these. Is that okay? So this would be the 7th entry. This would be the 8th. This would be the 9th. And then I would go down here, pick up the 10th, and then scoot back up. And when I scoot back up, because this would be 5 over 1, this would be the 10th. When I scoot back up, I got to skip the ones. I'm going up this diagonal, but I got to skip the ones I've already used, which I already used 2 and 1 and 1.5. And so I got to go all the way up here. This would be my 11th entry. Yeah, it's fun. It's fun. It's fun. And then you would go this way for the 12th entry and then scoot down that diagonal again, avoiding the ones you have already done. But in theory, you can make a list, right? A completed list. Cool, yeah? Yeah. Okay, these are countable. These are not. Gosh, I actually think I could get through this argument. I don't know. We'll see. We are just going to show that this is uncountable. The interval from 0 to 1, the numbers between 0 and 1 is uncountable. Because if this one interval is uncountable, then the union of all of these intervals will be uncountable. So we're going to pretend we can make a list. This is a good exercise. This is a proof by contradiction. Let's pretend we can make a list of all of these things, all of these decimals, and this again is going into a matrix. Maybe y'all will love linear algebra. So we're going to do this. I've got this sort of setup happening, and then this is going to go all the way down to the last one because I can make a whole list. So AN1, AN2, AN3, AN4, and then this would be ANN. So this is my completed list of all of the decimals between 0 and 1, and assuming I can write one, right? So what we're going to do, this is the Cantor diagonalization argument. This is what's in your textbook. What we're going to do is pick off the diagonal all the way down. So we're going to call that D. No, we're not yet. This is some new, I'm not going to call it anything. I'm just going to write it down. So this is A11, A22, A33, up to ANN. Now, the argument here is that this number is in this list somewhere because I listed all of the possibilities, right? So we're going to come up with this other element D. It's going to be D1, D2, D3, all the way up to Dn. Dn is going to be equal to 1 if ANN doesn't equal 1, and 2 if it does. Okay, so let me talk you through what's going on here. Oh, I shouldn't. I can't. Goodbye! Goodbye, I'll tell you on Monday. I know it's going to bother you the whole weekend.
I'll start counting.
Good. Make sure you can list all of the numbers between 0 and 1 by Monday.
Oh my. Well, so can we do a proof by contradiction by failing to count to?
Yeah, I think that works.
Okay. I can't do it.
Hmm.